All right, so when you completed that bingo sheet, what you should have seen was that the answers to the following questions matched with the solving spaces on the board. So question number 1 matched right here. Question number 2 was down over here. 3, 4, etc. So the correct bingo, which wasn't exactly what I was looking for, I was kind of looking for could you correctly match up the problems? But the bingo was right there. So again, take a minute, check your work, see if your bingo matches the bingo that was on there. Okay. And then we also did the trig and product rule handout. At that bingo board, are there any questions on any of those derivatives? Is there a derivative that you maybe couldn't find correctly, that you found but it didn't match, that you don't know how you got what you got? Okay. So then the next thing I wanted to look at was the trig derivatives. So that's these problems here. So oftentimes with trig derivatives, especially when applying the chain rule, we have a tendency to forget to take the derivatives of the inside. So just make sure that as we get into more complicated derivatives, that we make sure we take the derivative of the inside as well as the outside, and we're following all of our chain rule properties. So this handout kind of went back and reviewed those most basic rules, which is the product and the quotient. So one of the mistakes I've seen in the past is forgetting that the quotient rule is ho-de-hi minus hi-de-ho. So just make sure that when you're doing this, you continue to put the negative between those two parts of the problem. So again, for this problem, in order to find the equation of the tangent line, you needed to plug in pi fourths to the original function to get the y value of 1 when x is pi fourths, so that you could do y minus y1 equals the slope x minus x1. Then you had to find your derivative. Upon finding your derivative, then you had to plug in pi fourths to the derivative and get your final answer of a slope of 1. So this is why I continue to stress the importance of really knowing your unit circle, because we are oftentimes plugging in unit circle values to simplify and get down to a unique answer. The normal line is the line perpendicular to the tangent line, so our slope is going to be its opposite reciprocal. So whatever you get for your original slope, the slope of the normal will be its opposite reciprocal. And then down in 4, we were determining the coordinates of a function at its horizontal tangent. So a horizontal tangent line is when the derivative is equal to 0. So what we had to first do for these problems is find our derivative, and then once we found our derivative, we needed to set that derivative equal to 0 and solve for our x values. Now, these functions were a little bit more complicated, so you were allowed to use a graphing calculator to find those zeros. And I kind of stopped on letter B just in case we needed to work on finding those zeros on the calculator together. So I found the easy and obvious one if you took out your GCF. But to find the other ones, what you would do is on your graphing calculator, type in that function. So you'd go x parentheses x cosine x plus 2 sine x. And then in order to find the zeros of that function, what you have to do is after you get your graph on your screen, you need to use second trace, and you're going to go to 0. Move that into the light. There we go. So what I'm going to do is hit zoom, and I'm going to go to fit, which is down here at the bottom. So I can see right there that I have an x-intercept, which would be a 0 of the function. So we're going to go second trace, 0. And we're going to move our little cursor to below and above, and then a guess, which I literally just hit wherever I leave my above. And we see that the x value is 2070. And since we're in calc and we're using a calculator, we're always going to put 3 decimals. So we're going to go 2070.055. All right, I wondered. So I was in degree, and calculus we're supposed to be in radian, and I had been tutoring over break, and I was like, that's a really high number. So if you do the same thing and you do it in radian, you're actually going to get a different answer. So just make sure, there we go, that when we're doing this, we're in radian mode, because you wanted to see the oscillations, because the graph is going to repeat itself over and over and over. So what I was doing now is kind of creating just a box around one part of that, just so you can kind of get an idea of what it looks like up close and how many times the intercepts are going to go. And what you can see is that the intercepts are going through there at a continuous pattern. So if you look at a simple table, what you should notice is that it goes positive, negative, positive, negative, and that pattern is going to repeat. And then every time you see a sign change from a positive to a negative, that tells you that you have a intercept. So we could see how that pattern would continue to repeat over and over. So if I go 7, 8, 9, we can see that there is an intercept between 8 and 9. Then you see that there's another one between 11 and 12, etc. Page. So when you have a trig derivative to the 99th or the 1000th or the 96th, basically trig derivatives work in cycles of 4. So d to the 99, I divided that number by 4, because if you take 4 into 99, it would tell you what cycle of the trig derivative function you are in. And so basically, it's kind of like when you did functions of I. I'm going to move this. I don't like that it's on my hole punch. I must have done it and then moved it. So let's work through, we'll just do this one together again, just to give you an idea, because these are the type of questions that pop up on the AP exam and you're like, what? That's too difficult. I can't do that. And it's not as difficult as it may seem. So you're going to take the number 99, divide it by 4, so again, if you don't have a calculator, you're just going to do long division. So we get that 4 goes into 999, 249 times, with a remainder of 3. So what that means is that the derivative of cosine is the third cycle of our derivatives from the original. So cycle 1 is negative sine x. Cycle 2 is the derivative of negative sine x. which is negative cosine x. Cycle 3 is the derivative of negative cosine x, which would be negative negative sine x, or sine x. And cycle 4 should always get you back to your original, just like the powers of I. I to the fourth was always 1. So, the third cycle is sine x. Similar idea over here, but we have that factorial coming back into play, and we talked about a factorial a few times before, where if you have a repeating coefficient and that coefficient is getting larger exponentially because you continue to multiply by the derivative of the power above you, which is getting larger and larger in this case, then it's an exponentially increasing function, and we call that increase a factorial, and we call that n factorial. And then the multiple choice problems, these actually came off old AP exams that we're allowed to use publicly, just to try to start letting you see, okay, what do AP questions look like? So letter A was the answer to number 9. So for number 10, it says using this chart, we have if h of x equals f of x plus 2g of x, then find h prime of 3. So again, to find h prime of 3, you have to first find the derivative of h prime of x. So the derivative of that would be f prime of x plus 2 times g prime of x. So h prime of 3 would be f prime of 3 plus 2 times g prime of 3. So in this case, you would go to your chart. F prime at 3 is 4 plus 2 times g prime at 3, which is negative 1. So you have 4 plus 2 times negative 1, which is really 4 minus 2. So we get 2, which is letter choice B. In 11, it says if h of x equals f of x times g of x. So now 11 is testing your ability to do the product rule with two functions. So it's first times derivative of the second plus the second times derivative of the first. So it's really like saying h prime of 2 equals f of 2 times g prime 2 plus g of 2 times f prime 2. And then f of 2 from that table is 5. G prime of 2 from the table is negative 2. G of 2 is 1. And f prime of 2 is 3. So you get negative 10 plus 3, which is negative 7, which is also answer choice B. And then in 12, it says if h of x equals 1 over g of x. So now in 12, it's testing your product rule, or your quotient rule. So that's HO, so denominator, times derivative of the numerator. Derivative of 1 is 0, minus the numerator, which is 1, times derivative of the denominator, which is g prime x, all over g of x squared. So the first term cancels out. So you're left with g prime x over g of x squared. They don't cancel because g prime isn't the same as g of x. So h prime of 1 is equal to g prime of 1 over g of 1 squared. So you should plug both of those in first. So going up to your table, you get that g prime of 1 is -3, and g of 1 is 3. So you get -3 over 9, which is -1/3, which is answer choice B. And then in 13, now you're looking at the basic definition of the quotient rule. So it's HO g of x d high, so f prime x, minus high f of x d ho g prime x, all over ho, all being evaluated at 0. So we're really just looking at the 0 row right here. So you have 5 times 1 minus 2 times -4 all over 5 squared. A negative times a negative turns to a positive 4, so you have 5 plus 8 over 25, which is 13/25, which is C. So again, in case you need to see any of that work, or you need to go back and check it later, you can. So again, go ahead and take out that chapter 3, interpreting the meaning of the derivative in context. So this is all about, can you read between the lines? So it says the temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function w, where w of t is measured in degrees Fahrenheit and t is measured in minutes. At time t equals 0, the temperature of the water is 55 degrees. So that's our initial condition. The water is heated for 30 minutes, beginning at t equals 0.
Values of WT are selected in the table above for the first 20 minutes given. Using the data in the table, it is estimated that the derivative of W at 12 is 1.017. Using correct units, interpret the meaning of your answer in the context of the problem. So the original function is in degrees. So that's kind of like if you think about distance. The original function is in terms of feet. Its derivative is the change in feet over time. So for W in this case, it would be the change in degrees over time. So we're looking for an answer choice down below that reflects that kind of conceptually. So first it says the temperature of the water at time t equals 12 is, well, that's not true because we're looking at the rate of change of the temperature at 12, so it can't be A. The water temperature is increasing. So again, our derivative is positive. So if the derivative is positive, then we are increasing at a rate, so I like the word rate, of approximately 1.017 degrees Fahrenheit per minute, so I like the time, at time t equals 12. I like answer choice B. Now it's always safe to read C and D, but B hints on everything we're talking about. A derivative represents a rate of change. It is specific in terms of what it has. It has the answer as well as the time. And then again, this is positive. It uses that fancy word increasing. The average temperature, well, this isn't, W prime of 12 isn't average. That would be the slope of the secant. So it's not the average. And then the change, so I do like the word change, in the temperature of the water from 0 to 12 is 1.017. That would represent, again, the slope of the secant, not the instantaneous. So it's letter B. Number 2, go ahead, take a minute, read through that. Okay. So again, using the data to approximate a rate at which the temperature of T is changing at 3.5, show the computations that lead to your answer and interpret its meaning in the context of the problem. So, if we're looking for changing, again, we're talking about the derivative. But in this case, we're not looking at changing in terms of being given a function and a specific answer. Now we need to use our context to find 3.5. So I don't know 3.5. So to be given h prime of 3.5 equals -8/3, that's coming from the idea of taking 52 minus 60 over 5 minus 2. which is what we need to do because that represents the average or the slope of the secant. Because again, it says use the table to approximate. So approximate means that average or predictable. So to get h prime of 3.5, you're taking the numbers to the left and right, which is h of 5 minus h of 2 over 5 minus 2. So that hurts me and helps me, right? Because almost every answer choice has that. So it's really about interpreting what each answer choice is saying. They all have the temperature of the tea in the pot was decreasing.
Temperature of the tea in the pot was decreasing. Temperature of the tea in the pot was decreasing. Temperature of the tea.
So all of the beginnings are the same. Now it's all about the end. Per minute at time t equals 3.5. Well, it's not at this specific time because we don't know the derivative. So it can't be A. Per minute. Well, it's not per minute because it's changing. This isn't a linear function. Per minute at time t equals 3.5. Isn't that what I'm looking for? The approximation at that time. Because this is an interval. So I have a feeling a lot of students would be down to C or D. And the difference is this is asking me at this specific time. It's not that D is incorrect. It's just asking for this point in terms of this problem. So you have to go with letter C. So Duranda rides her bike along a road from home to school starting at 0 minutes and arriving at 12. During the time interval, her velocity in miles per hour is modeled above. So here's her graph. Find the acceleration at 7.5. So again, remember that acceleration is the derivative of velocity. The derivative of velocity represents the slope of the velocity. So we would want to know what is the slope at 7.5. So how do you find slope? Well, you take point A to point B and you find their change. So in terms of this problem, the slope or the velocity's derivative at 7.5 would be like v of 8 minus v of 7 all over 8 minus 7. Or 0.2 minus 0.3 all over 1. So negative 0.1. So remember it's velocity, so that means that this represents her change in position over time again. So that means that my answer is going to be like per minute per minute. So acceleration is the change in the miles per minute, for velocity being in my numerator, over minutes. So I'm looking for an answer that has per minute per minute. Any answer that just has per minute is out. So we can eliminate answer choice B. Even though the work for the math is correct, the wording is not. Same with answer choice A. The answer is wrong, but the wording is right. So we're down to C and D. So look for your differences. We have same beginnings, same answers, velocity decreasing, and here's the ticket. Are you decreasing by a negative value, or are you decreasing by a positive value? Well, if I'm decreasing by a negative value, decreasing by a negative is really like increasing, so that's incorrect. It's letter D. Okay, so just let's go on to the next page so we can do some actual math problems. I think you have the interpreting down. If you really wanted to know, the answer to letter 4 is D. So it says grass clippings are placed in a bin where they decompose. The amount of grass clippings in the bin is A of T equals. So this would definitely be a calculator problem, hence the calculator I put in the corner. And again, you can see that just because of the decimals in the problem. So the minute I see crazy functions, I'm thinking calculator. And then it says where A of T is measured in pounds and T is measured in days. Find the average rate of change. So average rate of change is slope of the secant. So average rate of change over an interval would be like A of 30 minus A of 0 over 30 minus 0. Average rate of change does not involve a derivative. Average rate of change does not involve a derivative. So you'd plug that in on your calculator and you get negative 0.196, and I kind of like to write an extra decimal, 8. And it says indicate the units of measure. So A is represented by grass clippings in the bin. T is represented by time. So this would be amount of grass clippings over the number of days. If you wanted to put that into words, it would be the amount of grass clippings in the bin is decomposing. Always try to use a word they use to start at a rate of 0.196 0.68 pounds per day over a period of 30 days. Find the value of A prime 15. So A prime indicates a derivative. So A prime of 15 is going to come straight from your graphing calculator. We're going to use that NDeriv feature. So you turn your calculator on, go to Math, go down to the option NDeriv. Hit enter. We're using variable x, so we'd put in x. Type in our original function. And then at the very end, you put the value you're going to find your derivative at. So in this case, 15. And again, indicating units of measure. Well, the derivative is the same as the slope of the secant. So it'd be amount of grass over days. And that says interpret the meaning of the value in the context of the problem. So that's kind of the sentence form it is asking for. So it'd be the amount of grass clippings is decomposing at a rate of, and since we use decomposing, we make this positive, 0.164, and then we know it's in pounds. Per day at day 15. You could also say at t equals 15 days. So, if you're still with me, so a student proposes the function p given by p of t equals, has a model for the temperature of the water in the pond, where t is measured in the number of days, where t is measured in the number of days and p of t is measured in degrees Celsius. Find p prime 12 using the appropriate units to explain your answer. So again, p prime of 12 is relatively easy. You're just going to your calculator, you're going to type in math, go to NDeriv, type in your function, and then type in the value you want to find it at. So we have negative 0.5494. And then explaining that in terms of our problem. So what that means is the temperature of the pond is, and the negative tells me decreasing at a rate, because it's a derivative, of 0.549. That is representative of degrees Celsius per day at day 12. And that's the kind of answer they're looking for on an AP problem. This would probably only be worth, AP free responses are only 9 points, so this would probably be worth 2. 1 for your answer and 1 for your interpretation. Okay, let's go on to straight line motion. So these were the type of problems where we did like motion along a line. So this is section 3.4. So it says a particle is moving along a horizontal line with the position function given below. Perform an analysis of the particle's direction, acceleration, motion, and position by completing the following number lines, and then kind of interpreting really what all of those number lines mean. So, in order to do this, we need to start with our derivative. So go ahead and calculate the derivative of that problem. Then we want to also find our acceleration. Which is the derivative of velocity, which is the second derivative of position. So we found our velocity and we found our acceleration, but it asks us to give an analysis of the particle's direction. Well, in order to get an analysis of direction, we need to really be able to know where does the function change direction, which means we need to find the zeros of velocity. They're all divisible by 3. I would factor out a -1. And that gives at time t equals 4 and t equals 2. So what that means is that the velocity changes direction at 2 seconds and 4 seconds. So those are considered key points. We'll know if it's moving left or right by finding out if the velocity is positive or negative between those key points. So we need to know what is v of 1, what is v of 3, and what is v of 5. So v of 1 is plugging in here, negative, negative, negative. So 3 negatives make a negative, which means it's moving to the left. Plugging in 3, we get negative, negative, positive. So negative times a negative is a positive, times a positive is a positive. Remember, we don't care what the value is, just its sign. So it means it's moving to the right. And plugging in 5, negative, positive, positive, which gives a negative, which means it's moving to the left. So that gives me direction, acceleration. Now to look for motion, I need both acceleration and velocity. So what we're going to do is find the zeros of this. So we get it at time 3 seconds. So I try to line up my 3